In this video, we'll generalize our definitions of the trigonometric functions to arbitrary sized angles. You may recall that what we did with right triangles only applies to angles that are acute, less than 90 degrees. And we want to generalize this to angles that may be bigger than 90 degrees or even negative angles as well. In order to do that, what we're going to do is put in the usual coordinate system, x and y-axis, and then I'm going to draw a circle centered at the origin with radius r greater than 0. So the center is at 0, 0, and there's some radius r, some positive number to that circle. So r is the distance from the origin to a point on that circle. That point has coordinates, x and y coordinates, so I'm going to label them x and y. And remember, the condition required to being on this circle means that x and y have to satisfy a certain quadratic equation, which really is just, in a sense, the Pythagorean theorem. If I look at this point xy, it is on the circle if and only if the following condition is met. If I square the x coordinate, I square the y coordinate and I add them together, it better be the square of the radius here. So in other words, x squared plus y squared has to equal r squared. And in fact, that is the equation of a circle of radius r. It's a quadratic equation that x and y have to satisfy. What I've done now is drawn an angle, and I'm always going to start when we take this point of view with the coordinate system, with the xy coordinate system, to start the initial ray along the positive x-axis as I've drawn it here. Then I'm rotating some amounts to get an angle theta, and its terminal ray is ending here. When we do that, we're going to say that theta is an angle in standard position. So just make sure you understand what I'm saying. Positive x-axis is the initial ray always, and then we rotate counterclockwise for positive angles, or we'll rotate clockwise for negative angles to get to the terminal ray of the angle. So this is called standard position. Associated with that angle are 6 trigonometric functions. The sine, the cosine, and the tangent are the ones that we talked about in terms of right triangles. What we would have done for sine is to take the opposite, which is in this situation the y-coordinate, and divide by the hypotenuse, which is now the radius of my circle. So sine will be y over r. Similarly, cosine will be the adjacent, or the x-coordinate, over the radius, the hypotenuse. And then tangent will be the y, the opposite, over the adjacent, the x-coordinate, so y over x. These 3 functions also have reciprocals that have names, and it is defined to be that the cosecant is the reciprocal of sine, so it will be r over y. Secant is the reciprocal of cosine, so it will be r over x. And cotangent is the reciprocal of tangent, so cotangent of my angle is the x-coordinate over the y-coordinate, not the y-coordinate over the x-coordinate. These are just 6 definitions for each angle, regardless of how I draw it, wherever it happens to intersect this circle. I look at its coordinates, I look at the radius of the circle, and I form these 6 ratios to get the trigonometric function values of that angle. Let's look at a specific example. Let's find the trig function values of the angle theta that I've drawn below. I've drawn it in standard position, starting with the positive x-axis. Terminal ray, it's a positive angle because it's rotating counterclockwise, and that terminal ray apparently intersects the point -2, 3. So x-coordinate -2, y-coordinate up 3, and that point -2, 3 is on the terminal ray of my angle theta. I don't know what the angle is, but I do know a point on its terminal ray. We can find the radius of the circle that seems to be intersecting that point centered at the origin by using the standard Pythagorean relationship. If I square up the x-coordinate -2 and square it, be careful with the order here, it will become positive. And then if I square it the y-coordinate 3, I should get the square of the radius. That's what we were saying over here, that the circle should satisfy this equation here. And we're missing the radial distance here, so we're going to solve for that by plugging in our known x and y on the circle. When I evaluate this, I get 13, so r should be the positive square root because it's a length. It should be square root of 13. We can now construct the sine, cosine, and tangent of my angle theta. To do that, I take for sine the y over the radial value, so 3 over square root of 13. I take x over the radial value, so minus 2 over square root of 13. Notice that when my angle is rotated so far that it ends up in the second quadrant here, that the cosine turned out to be a negative value because the x-coordinate of that point, or really any point on the terminal ray, would be negative. And that's why we're seeing now a negative value for the cosine of the angle. The tangent is the ratio of y to x, so it would be 3 over minus 2. And again, it turns out that for this specific angle, one whose terminal ray lands in the second quadrant here, because the y is positive and the x is negative, their ratio, their tangent, will be negative as well. You can simplify these values by rationalizing the square root of 13 in the denominator to get what are typically more acceptable answers, although I don't really care one way or the other, and then minus 3/2 for the tangent of the angle. And as we discussed above, each one of these has a reciprocal, so the reciprocal of sine is cosecant. If I just flip the fraction over, I'll get its value. Cosecant is root 13 over 3. The secant of theta is the reciprocal of cosine. It's just how it's defined. And tangent of theta is, or cotangent of theta is the reciprocal of the tangent minus 2/3.